Inshallah.
So, yeah, that this is of course a said Turkish. So then, so I did everything. Enable security. I did.
So
I did. I guess I did everything.
yes, yes, good.
Yeah, good. Okay. So now we can start after 2 minutes, and so then we will have an exam. I will let you know in the end, maybe in the next week and or after 2 weeks when we will have an exam. So the exam will be in the same manner as was before. So that I will try to make it 2 groups, and it will be maybe a little bit difficult questions, but everything will be in the framework what you learn in my lectures. So as I said, the goal was to prepare you for the future. If you would like to work, if you are a mathematician, to work with biologists, if you are a biologist, to work with mathematician or the doctors. So the purpose of this talk and this the series of lecture was namely in this direction. And so you will I will let you know anyway. Okay, so then I guess now the 2 p.m. in we can easily start. So do you know? Could you look this? It's good scene, or I can switch this. So could you Mohammed or somebody else, could you tell me which the degree of light give you a chance to see the better? This better or this better? Which one?
This
Or this?
switch off all the light ho jam.
Okay, this is all light.
Okay, now it's okay.
Now it's okay?
Yes.
How about that again? It's okay now? Okay, very good. So let's just start our lectures. And if you remember, last time I started with the very simple stuff, but today we will deepen on this. So that, if you remember, we considered very simple one-dimensional questions. So if you have the one unknown solution, if you are looking unknown the function y dependent on t, so if you have the one equation with this initial data, we are saying this is the one-dimensional system. If you have instead of the 1, 2, for example, you see, if you have 2 equations, when the right-hand side depends also only on 2 variables, then we will call this, this is in general, so the 2-dimensional system, because you have 2 unknown. If you have, for example, n unknown functions, then you are saying the n-dimensional system. In the case of partial differential equation, we are saying the infinite dimensional, because we will have, instead of this variable 1, and we will have instead of this n equation, the formula, when you are saying infinite dimensional dynamical system or infinite dimensional system, then you will have not the finite component, the u1, un, you will have the infinitely many components. This is the, roughly speaking, infinite dimensional the systems or infinite dimensional dynamical system. Now, but within this course, in order to give you just to prepare you for the next lectures, maybe in the next semester for infinite dimensional system, you have to know what was before as a Buddhism philosophy. So what was before, what we are, and what will be future. And therefore, we will start with as you see during the discourse this semester, I restricted myself to the finite dimensional systems, or sometimes we are saying finite dimensional dynamical system, because we are interested in the behavior of the solution. So the solution of this equation, again, let's consider the one-dimensional system. So dy of dt is equal f of y. So this is the given function. The f is given. We are looking for the function, this is unknown function, y of t, which is dy of dt is equal fy. And if you are taking the derivative of the function, it must be identical when you are putting the y of t to the given function. And since we are interested in some biological or biomedical processes, we have to know that where we started. And actually, this is a mathematical idealization, so-called the initial value problem, because usually, as in the case of the COVID and many disease, we don't know exactly when this disease or when this process is started. This is something. It could be, as the many people now, many government, unfriendly government to China, saying that it was made in the laboratory, and then you know that when you started. But it could be also as a nature. It could be due to some ecological or environmental problem. So then it was a very unfriendly environmental problem that this kind of the disease started. It's in the history we knew that some disease has a nature due to the natural process, and some disease or some biological weapons, if you want, they started in the lab. Therefore, in general, we don't know. So the initial data, but as a mathematical idealization, we are saying that when we are speaking on the equation, differential equation, that means we are always thinking that the initial data, y of 0 is given, and then we are looking for that. Now the equation to the audience, last time, so if you have this equation, in general, it doesn't mean that this given equation has either solution, or if they have a solution, the solution exists unique way. So last time I asked you to show that this equation, do you see that on the blackboard?
Evet hocam.
Yes.
Could you say what is the solution? I say that this one of the solution of this equation is identically 0. Y of t is identically 0. Because if you take the derivative of 0, it will be 0. If you take the square root of the 0, it will be 0. That means this satisfied, and the initial data is the 0 as 0. What will be the second solution? If somebody looked at, I asked to look at how it looked like solution. Could you say somebody from audience? No, it's silent. The second solution will be t squared over 4. So then you can easily, you see, the one solution will be this. The other solution, I am saying that this must be this. Indeed,
Hocam, have you differentiate this equation?
So what does it mean, the solution of it? Why this function is the solution of this equation? Because if you have to take a differentiation, the left-hand side, if you put this function to this equation, the left-hand side must be equal to the right-hand side. If you take the derivative of the left-hand side, we have dy of dt. If you take the derivative of this function, it will be t over 2, right? Because derivative of t squared will be 2t, 2 will be cancelled with 4, it will be t over 2. So the derivative of this function, the left-hand side will be t over 2. But if you take a square root of t squared over 4, since we are dealing with a positive solution, it will be t over 2. So that means, and then divide the point 0, if you take the t 0, this guy will be 0. So this completely satisfies this assumption. They show that usually not necessarily that given the differential equation has a unique solution. And in biology, in medicine, and in many the evolution processes, we always need to deal with this unique solution. We are interested in the processes, doesn't matter in fluid mechanics or population dynamics or some disease propagation. We are always interested in solution will be unique. So that not necessarily that first of all, if you have some equation, dy over dt is equal to fy. First of all, it doesn't a priori means that this equation has a solution, right? Like in the school, if we are looking for the square root in the school level, in gymnasium level, square root of -4 or the negative number, you will never have a solution because you don't know what is the complex number. So if you have a sum equation, which is written for one, I am speaking now for one-dimensional thing, but if you have this, then this is the first of all, it doesn't necessarily mean that this will have a uniqueness. Also, this solution will exist. We don't know, but it could exist, as in these simple cases, but it could not be unique. And therefore, since we are interested the existence of solution and uniqueness of solution, in one case, and also in general, in n-dimensional case, so there is a theorem which you have to learn in the previous courses in the undergraduate level, that if the given function f1, fn, this is for n general, or for n is equal to 1 for given function f, or in the n is equal to the two-dimensional system, which we are really interested in, because I told you that. So we will see that this is we will mostly restrict ourselves for the two-dimensional cases, which will be on one hand very restrictive because, but on the other hand, it has a very nice feature because some of the very important processes. Disease modeling or the chemical reaction under some circumstances can lead to or can do have a reduction to the system. And then I will show you that why this the system is very important. I showed you that this is the molecular enzyme dynamics. I showed you also the COVID-19 can be discussed in the framework on two-dimensional system. Therefore, we know that so we are interested in uniqueness of solution. Therefore, this simple example shows that in general we don't have uniqueness of solution, and then so the very natural question arises. So when we will have the first of all, the existence of solution when solution exists, and then when it will be the existence of solution is vitally important because you can do numerics of the equation, and if the equation has no solution, your any numerical or any patterns appears via your numerical simulation of these or in general of these doesn't have any meaning because mathematically you can prove that solution doesn't exist. Now, therefore, arise if you are trying to deal with the biological people, if you are trying to understand to help the experimental biologists or experimental chemistry or the doctors, then you have to have at least you have to try to prove first of all the model under consideration, which you receive either from the experiments or from some the connection with the doctors. They will have a solution, and therefore, if we have it in general, in order to have at least the local solution, at least the solution exists for some small time of t, then one of the sufficient conditions will be that F1, Fn will be Lipschitz, global Lipschitz. So if you the name Lipschitz you don't like, then you can just say that the function F1 and Fn should have at least the partial continuous one partial derivatives. That means that if the F1 will have a derivative with respect to U1, because F1 has a generally, because if you are considering general, F1 will depend on y1, yn, or if you want U1, Un, Fn it will be depend on general U1, Un, and then if the derivative F1 with respect to U1, derivative F1 with respect to Un exists and is continuous, then and also the Fn, the partial, we are saying partial derivatives. So if you have for example, n is equal to, you have your function will depend on the two variables. If you got y1, y2, that means that your derivative f1 with respect to u1 should exist. Your the derivative of f1 with respect to y2 should exist, and as after the derivative, this function must be continued, which is not the case here. If you take y over 1 over 2, its derivative will be just the 2 times, if you want, so 1 over 2. So if you take the derivative of this guy, so then if you take the derivative of this, then it will be 1 over 2, the 1 over square root of y, I guess, if I correctly remember. Right? But you have to know much better than me, because the students always taking the derivative much better. So that if you take the derivative of this guy, then it will be the y power alpha, it will be equal to alpha times y power alpha minus 1. It will be the y power minus 1 over 2, and then it will be that. You see, this function, so that you take the derivative, but this derivative at the point y is equal to 0 is not continuous. It's equal to infinity, right? 1 over 0 is infinity. Therefore, this function doesn't satisfy the assumption what we say, that the function f1 must have the derivative which is continuous. But this function is not continuous, therefore it cannot be considered in the framework of the Lipschitz or the function. That's the point why this solution has no the unique solution, and because in order to have one of the sufficient conditions must be likely. Okay, so this was the point that I discussed with you last time, and now then in general, as I said, we will have the derivative. If we have the two-dimensional system, we will have this, and if we will have the n-dimensional systems, we will have this. And last time I discussed with you also the steady state. And then, assume we have the system is a given. System is a given in general, and then we are saying that the point, because the f1, fn in general depend n variable. So then, if you we are saying that this the vectors in general. In the case n is equal to 1, this is the only one scalar. But in the case, if you are considering the n-dimensional system, so you will have, if you remember in Voltaire, you have 2 variables. And then if you have equation, if you have the ordinary differential equation, that means if you have a system, the point, so this is the point that means the vector q1, qn, because you have an n equation. It's called the steady state. Again, please, this is the, you have to concentrate on all this stuff, because this will appear also in the exam. And in an exam also will appear what you learned before, so that in midterm exam you have to some good words, and then we will have also The final exam will consist of what you learn in the before midterm exam afterwards, and the given point we are saying is equilibrium point if this the right hand side, if you are writing the equation, the right hand side is equal 0. Then I will show you then how it works. And to know this equilibrium, is very crucial. So this is a crucial for example, for the engineering people. This is very crucial for the economical people. This is crucial in every other social life. Equilibrium. So then, if you just say in the Turkish language or in the real meaning, it will be the minshikir. That means that on everything. So it's equilibrium. But and then nothing bad happens. So everything is equilibrium. You didn't lose anything and you didn't gain anything. So minshikir. That if you would like to have a little bit more minshikir, that means that there is the concept of the a little bit or more minshikir is called the stability. That means you have the equilibrium, but you are a little bit happy than equilibrium. That everything, if you, for example, if you have your temperature is good, and also you have a very good the weather, then it will be, then you are very happy, you can go to swim and so on and so on. So everything, the equilibrium plus something, which means the stability, stable. And stable means that this is your good mood or your good life, it will be continued a little bit. If you are saying the local stability, that means that if you have to be the more pragmatic, if you have money, and then in the next year or next 2 years, you will have a little bit of profit. So then if you have €100, then you will have during the next 2 years, you will have 110 or 120, but no less than the 100. So this means that your life will not change, and it will change a little bit, but in the positive direction. And then if the unstable, that means that you will lose. So the people always trying to avoid have the unstable, but this is a life. Then we are conjugated with the stability and instability equations, and I am pretty sure that even today is January 14. And last year at this time, I was in Canada giving the lecture on infinite dimensional dynamical systems, and even in the January 14, we didn't know on such a COVID. We heard that something happened because the World Health Organization say that this is in China they observed some new kind of the COVID, new kind of SARS, more precisely SARS. It was the name, but it was not contagious. And then we don't care. In Turkey or in Canada and the US, we don't care that it will make some bad impact. So they will follow that. So then we look forward. And but later it was discovered it was the very unstable situation. So then in February 14 and 15, the last year we had, including me, very serious 2 days workshop with the immunologists, with medical doctors, epidemiological experts. So already we started to have some information on COVID, and then we give a suggestion to the Canadian government that please take this very seriously. You have to order wearing masks, not the closed economy, but wearing masks and the social distance, because we can build it. Do you remember I discussed with you the two-dimensional COVID model, COVID-19? Many people considering at least three, and then you will see that why I don't like the three-dimensional. Of course, I am expert on infinite dimensions. That's much worse. But then, in the case of one, if you have the possibility to reduce system to two dimension, it will be much better than if you will reduce to to three. Then you remember. Let me just say that. So you remember we had the enzyme dynamics. It was 1, 2, 3, 4. It was the four-dimensional system, and due to the conservation of mass, we reduced this to the 2. This 4 we reduced to the 2. I say that we will happy if we will reduce this 4 to the 3. And but in 3, so we don't have too much information than in the case of 2. But it will be the ideal if you will reduce to the 1, and then but sometimes it's impossible. Then I was maybe it's not modest to say, it could look like the gay mutawazi. So then I found the systems in biology, which is infinite dimensional system, which cannot be reduced to any finite dimension. So it was a completely new direction in biology and in mathematics. It was such a kind of groundbreaking result. But this is not in what I am going to speak. I would like to give you introduction to such a beautiful area, which can be said that the finite dimensional dynamical systems, although I will touch also some kind of the infinite, the partial differential equations, so then which arise if you are trying to model some, not all, some interesting biomedical process. Okay, so then as I said, if we have the given n-dimensional systems, in n is equal to 1, it will be one equation, n is equal to 2, it will be this. One can see actually that this on the table. Do you see that group in the table? Yeah. Mohammed, it's readable?
Evet hocam.
Yeah, very good. And then you have to just try to you have to try to deal with that. Now, as I said, to analyze this is usually the biological systems or biomedical system or in our life is a nonlinear. That means this is the function f1 as this simple example shows. So this is a nonlinear. So this is not the y of dt is equal y or alpha time y. So this is when I'm saying the linear, that means that the given function is a linear function. So the graph is the straight line. But this is, if you know that this is the graph, it will be like a nonlinear curve and many other things. Or here it will be, instead of dy of dt, it will be sine of y. If you know the sine of y is not straight line, so this is such a kind of oscillation. So, okay, so then in order to, what we would like to handle with the system, as I said, in order to study, in order to understand the behavior of the system, we know from the differential equations, or we know differential equation in which semester you learn? Second. The second and third years, you know what is the differential equation. I'm speaking for mathematicians and for the related physicists or chemistry people. Anyway, so but my lectures is not only for mathematicians, not only for engineering, not only the people from fundamental sciences. So my lectures. So this meeting will be in 10 minutes. Could you inform that? Yeah. So now my lecture is more oriented for all people, for economists, for the biologists, therefore, and also for mathematicians. Therefore, we know from the, even for 1D, for a simple equation, when f is a nonlinear function, we know from your second semester or third semester that you cannot, even such a simple ordinary differential equation, to find the formula of the solution. For this simple, of course, we have. You see the y of dt square over 4. If the y of dt it will be sine, then of course, then the solution will be minus cosine of and then many kind of things. You can, if the y of dt it will be the y, the solution will be y of t. It will be exponent of power here to the t. So then for the simple functions, we can find the formula, exact formula. But in the more general case, if you have a more complex function, which is in reality the right-hand side, if you have a right-hand side, they describe interaction of the species, and this interaction of the species in our nature is very complex. And therefore, they don't have such a simple form. So it could be on such a form which cannot solve this. We can say, because if you have the function f on the right-hand side, so if you have this equation or this equation, if the f1 has a partial derivative with respect to y1 and partial derivative with respect to y2, and this will be continuous, partial derivatives are the same with f2, then we can say that this equation has a solution. But the existence of solution we can guarantee from this theorem. But for in application and in order to deal with the experimental biologists or the medicine, they don't care, as I said. So the physicists know this. So they know much better than the mathematician that this solution, this exists. And biologists and the experimental biologists, they know that. So what they are doing in experiment, they have seen some features of the output. And they are most interested what will be happen. If you don't have a solution, in most cases we don't have, we have a solution of the equation, but we don't have exact formula of the solution. So if you don't know exact form, then you cannot say too much, because the experimental people, they are interested how if they will change the parameter of the equation. So in this case, if they will k1, k minus 1, k2, how the system will change. So these are the people interested in. So because behind of k1, k minus 1, k2, which are the reaction rates of this chemical, the processes, they are conjugated with a lot of money. And they are interested in how to minimize of the amount of the money, how to have the profit with the small. This is quite natural. And if you write the equation for this, you can guarantee that this solution exists. But they know this is in advance. They are interested how the solution will depend on k1, k minus 1, k2. And then since you will have the equation, and even if you will reduce to the two-dimensional or one-dimensional, you cannot have the in general exact formula. And as a result, you cannot say too much dependence of the solution k1, k minus 1, and k2. However, in the 2 centuries ago, so the Henri Poincaré initiated a very important approach to in mathematics and also in differential equation, which is called the qualitative behavior. So in other words, in order to say much more on the process which the differential equations is described, you need, you don't need, if you have the exact formula, you are happy. So then you can say much more. But if you don't have usually you don't have the exact formula, what you can say more then depends on the solution, depends on the process of the parameters. And to this end, Poincaré suggested the concept of the qualitative behavior, and this qualitative behavior will depend, now I will show you, it will depend on the concept of equilibrium. So this is if you have the equation, differential equation, you are saying that this is the equilibrium. If this is the right-hand side 0, I will show you then in examples in a minute, and then try to find the eigenvalues of this. So the eigenvalues computed on this equilibrium. So for example, if you have this process means, when I'm saying process, this is for the people, those are not mathematicians. So for the mathematicians, that means process, behind of the words process or biological, chemical, physical, you have an equation. And for those are not dealing with experimental biologists, so are dealing with the chemistry, they have the process, they have some reactions, they are doing some experiments. So the word process for those are not mathematicians, that means this is some experimental evidence or some information. And for us, you can write the equation. And now the goal is to understand the process. That means understand the process from the experimental biologist. For the mathematicians, that means to analyze this process around of the equilibrium. So I give what is the equilibrium. That means to find the solution, then all of the part is equal 0. Right-hand side is equal 0. And this is usually the polynomial. And then you know from even in the school, when you were 10 years or 12 years or 14 years, that if you have a polynomial degree n, then this will have the n solution. All right? And therefore, so then you will have a solution of this algebraic equation, and then you can find. It could be that you don't have any equilibrium at all. That means that it could be that this equation f1 is equal 0, so that f1 is equal 0, fn is equal 0. So this is the equation for equilibrium, that in the right hand side. 0. This is a system. It could be that, you know, from the school, not any system has a solution. So it could be that this equation has no solution. But if this has a solution, we will say that the system possesses equilibrium. And now then we are interested in, so you see, if you have an equation, equilibrium, then this equilibrium will contain information on K1, K minus 1, and K2. So then this, because if you write the equation for this, if you remember my two or three lectures before, so we have the precise information on the right-hand side. You will find this, and then based on this equilibrium, you are considering n time n matrix, which is called the stability matrix. So you have a process that's from this part.
Yes.
Good. Okay, so then that means that if I go, but today I will use the standard, okay?
Okay.
Okay, let's just start. Continue our discussion. I said to you that, so our goal, if we have some, for example, this is a very good example from Enzyme Dynamics, and then you remember that we reduce when we have a 2, we have a 1, we have a 1, so that this was what kind of things could appear as an exam. So that this is for enzyme dynamics, we have here the only 1, so we don't have 2 here. So let me just say we have here, or in the lecture we have here S plus E0. So we had this kind of the reactions of the substrate and enzyme, and then so we had this kind of very 4-dimensional system. We use this is 2 using the so-called the mass conservation. Now today I will speak on the systems and 2D systems which we know, and then so as I say that we cannot find in general we cannot find exact formula of solution. So we don't have exact formula of solution, even such a very simple 1D equation. So that now let's consider the 1D. I would like to show you what I mean that. So this 1D equation is usually the people are writing in mathematics y prime of t is equal f y of t. So this is the y of dt. This is a derivative. People writing like this, and y of the 0 is y0. This is the given. In the biological process or biomedical process, usually we are considering that y0 is not negative because the population cannot be negative, and then and also the evolution of this. So usually this kind of the assumptions is coming from biomedical. So we are dealing with biomedical requirement because usually we are dealing with the evolution of non-negative quantities. That's why we always assume that so we are dealing with when the solution, when each of it is non-negative and solution, we are looking for the solution which are negative. All right, and then, as I say, we don't have the exact formula for the solution. In general, we don't have in general, and therefore, as now I would like to show that it's if you would like to understand the process, not necessarily. You will be very happy. We will be very happy if we will have exact solution, and then we can we see the exact solution like in some sense. If we are doctors, you are looking at your patient. You know his or her face. You see that directly what kind of the defect or what you have to change if you would like to make some surgery. So you know the face, and then you know in which part something happened, in which part something swelling, what is there with the eyes, you know. But sometimes usually you don't know the face. I'm speaking in general. When I'm saying that we don't have exact formula, that means we don't have the exact solution. But Poincaré and the qualitative behavioral solution, qualitative behavior of solution. So this is the more appropriate for understanding process and more appropriate for I would say, for the biologists and for the biomedical, for engineering people, and for us also the mathematician. And what does it mean when I am saying that we are trying to, what does it mean the qualitative behavior? And now, let me just, so the qualitative behavior or understanding to the process of the biomedical process, that means you have to try to make it will be something cartoon picture of the process, cartoon. So that if you have an equation, as I said, this is a given, and this is also a given. And having this, the qualitative behavior means you will obtain immediate information, not solving the process, not solving the equation, which is the, in order to make, you have to take integrate, and then not all integral you can compute. And therefore, if you go the direct way to solve the equation, it will be, you will be restricted a lot because you don't have an exact formula of solution. You know the solution exists because in order to show that the solution of this equation exists, for you it will be enough to know that the derivative of this function exists and continues. So that it's enough, and if you have this equation, it's enough that f prime of y, so the given function has a derivative, and this derivative is continuous function on y. So it's enough. So if the function is continuous and enough, you know that you have a solution and unique. But you don't know exact form. Exact form. You don't know exact form. But since you are interested in a solution, how they are look like, as a result, you know what is the process. The idea is the following. Let's just, for simplicity, consider the following: the f of y, the given function, has the form, say y minus. I'm just giving a simple. You can. I will show you several things. Say that 10 minus 1. It could be here 2, it could be 5, anyway. So let's just consider the fy of this equation. That means, so we are interested to solve the equation. So we are interested to solve equation y prime of t. So we are looking for solution of the following equation. Y prime of t is equal to 10. Minus y of t time y of t. So if I am writing y of t before or then doesn't, because a times b is equal to b times a. So then we are looking for solution of equation the following, and say the y of the point 0, say the y 0. Arbitrary number. So could we make a little bit black on that? And then now, so if you will try to solve this equation, which you have to learn in your second semester, then you will have a difficulty to integrate this. And then, in order to understand what's going on, then you have to just solve this equation to have the formula for y of t. And then you have to make this. But the other way to obtain much more information without solving this and saying much more is the following, which is called the phase diagram. So phase diagram. So this is this phase diagram is very important for biologists. So for biologists, for medical doctors, for the chemistry people, they should not know how to integrate the equation, this differential equation, or more general, the two-dimensional system, or N. They don't care if they know the very good knowledge in the school. That will be enough to make their experiments, and then with the help of mathematician to see the equation, how it looks like the equation, and extract information direct from the equation, not solving them. Even we are mathematician cannot find the exact formula. We cannot solve any equation. Then we cannot ask the biologist or the medical doctor to solve them. But we can give some very useful information for them, and they can check itself. So this is the goal of the phase diagram. Now, in this sense, let's consider this. Phase diagram means that if you are looking at this, and in our case, f of y is there, so that means you have to consider the phase diagram means you are considering equation, the following, the plane, which consists of the y prime and y. So you are considering the following, which is called y prime and y. Usually we are considering the solution of this equation, or the solution in general of this equation is y of t. This is the solution. But now I am speaking on phase diagram. The phase diagram means that if you have equation, which one was the new one? This?
No, because it's not.
So we have to wait a little bit.
No, this cannot open.
I cannot open. This maybe you can do that. Okay. So then this is the phase portrait or phase diagram. This is what the solution. We will obtain information from these two here. So the y prime, the y. So this is the phase point. Now we know that we are looking for solution. Y prime is fy. That means here y prime is this. If y prime is equal to that, that means y prime is a function from y, because we are looking for a solution of this. And then how it looks like, now I would like to make a graph of this. So how it looks like the graph of this function, 10 minus y of t times y of t. Because y prime is equal to that. So y prime is equal to that, because we are looking, and y, this means depending on y prime from y. So y prime is equal to this function. Now I have to make a diagram of this. That means at the point 0 is 0, this function. At the point, let's say 10, when y is equal to 10 is also 0. And then since this is, but this is in the school, you can even, since the y times y it will be, so this function is equal 10y minus y squared, all right? So if you multiply, thank you very much. And then that means this will be, the function will be like this. So the graph of this function will be like this. And now I have, so what is the equilibrium of this equation? Equilibrium of this equation, that means the right hand side is 0. The right hand side is 0, that means y must be 10. So this is one equilibrium, and the other is 0. So now we have a two equilibrium, and we know that this is the upper function f of y, which is equal y times 1 minus. Now we would like to know what's going on. So this is my phase diagram. Now I am interested in the solution of y of t. First of all, I am looking the behavior. How to I don't know exact formula of this solution, because in general I cannot integrate the equation. So of course you can try to solve this and to find exact solution of this This is called the logistic equation, and here the 10 is called the carrying capacity. But anyway, so that this is the situation where but you could have here the much more complex function, 10 minus y squared of 2 and the y power 5, for example. Nobody excluded these things. I'm just looking at this, and now the idea of the phase diagram, or idea of the quantitative behavior is the following. So now let's just look. Now I am trying to understand how behave my solution. How behave my solution? I cannot say the exact formula, but now I am trying to understand how they behave my solution around equilibrium. And this is equilibrium, as I said, that this is mu q. So then how my life or how the disease will be propagate around of the equilibrium. So now therefore this is 10 was the equilibrium, and then I am looking to sound the point nearby of this equilibrium. So then now I am taking y0. So this because I am considering now y0. Sum here. You can take here. It's up to you. Then I am looking at the y0. So the value of this here, f at the bound y0 is a positive. All right. So this is f y0. So this is a positive. So this is my function, the positive. If this is a positive, because here is a positive, then since the y prime at this point, it will be fy0, which is a positive because at each point this must be. Then that means that this function is monotone increasing because the derivative is a positive. We are taking the y0, and then we would like to know what is the derivative. But you know that y prime is equal to fy. So this is, you know, that this is f. Therefore, the value of the fy will give you information on the derivative of y prime. That means if y prime is a positive, if you have the derivative is positive, that means the function is monotone increasing. And that means the value of y of t in the nearby of t0, it grow up. Grow up means this direction. When you are grow up, it means this direction. That means that nearby of the equilibrium on 10, I am very close to this value. This huge information. You are not solving. You are just looking at the equation and then having the phase diagram. You are again. This can be done only for if you have a this. You see, if you have a 1D, then you can take y prime and y. So I'm speaking only for this, the 1D system. Now, so you know that this is the cartoon, the solution goes to direction of 10. Right? Now, so, but this is the phase diagram, give you our information. Now take this point. If you take the initial value here from if y0 will be here, then the value, you see, this is the negative. That means if you take from here, if y0 is negative, that means y prime at this point will be negative. If the derivative is negative, that means that the function is monotone decreasing. That means from here I am coming decreasing. That means y become less, and then that means I am going in this direction. And then you see, so when this error from the 10 is equilibrium, because when y is 10, this fy is 0. And then you see, then this equilibrium, we have two equilibria. One equilibrium, the one of t, is identically 0. Other equilibrium is 10. So now I have information how my solution behave at nearby 10. Right? Now you see we have a huge information. Now I am showing you how this phase diagram gives information on our solution. This picture for us very important. But this picture we can receive without integrating this. So huge information. Integration not always bring exact formula. That means you don't have exact solution, exact formula. You don't have a solution which will be useful for biologists, which will be useful for, because you don't have exact formula. But such a simple understanding of the phase portrait, which is based information only by zero and initial data and the given fraction, give you much more credible information, the behavior of solution. So on this cartoon say that if it will be 10, so because this is the value of y. Now, so this is the y prime y, which is called phase diagram. This is our real solution. That means that our solution nearby, if the y0 between 0 and 10, so this is minus 0, and the solution converges to 10. Because the error going this direction, because the f is the positive and the function will be monotone. So you see, then this. If it will be initial data will be above, that means from here, the solution converges to 10 decreasing way. That means we know without solving this equation, the behavior of solution around this equilibrium. Huge information. That means solution around of this converges to the 10 in this way. Huge information. That's the information that if from above and from below the solution converges to equilibrium, this equilibrium is called stable. Stable means that the error from both sides going in the direction to the equilibrium. You see, if y0 will be here, the error will be this, and if y0 will be here, it's going to that. And now let's consider this. The other equilibrium was 0. Now I am taking the initial data from the nearby of the 0, and I am looking for the value. Value is a positive because this is the function y prime is equal to fy. And fy, which is this function, fy, which is this function, at this point is a positive. That means that the error will be away from 10, away from 0, because this is a positive. If you take the y0 from here, then you will have here, again, if y is a positive, that means the direction will be in this way. And therefore, the solution, if nearby of the 0 equilibrium, solution will go in this way. If you take this from here, if you take the y0, the less than 0, then the f of y0 it will be negative. That means the function is monotonely decreasing. This will be that. That means error around of 0 going away from 0. Around of 10, you see that from both sides coming to 0. Error coming to 0. Therefore, this is stable. And when then you see around of the 0, the error from the both sides going away from 0. Therefore, 0 is called unstable. And this information, this cartoon from the phase portrait, give you behavior of the solution around the equilibrium 0, around the equilibrium 0, around equilibrium. So this is our solution. And this is the cartoon. Now, let's in order to make with you the other picture, let's consider the what? Yeah. And now let's consider the function. Let's consider this equation where we have the other function, and then you will see the picture. Now let's consider the y prime of y of t is sine of y of t. Let's consider other equation. Such a difficult equation, very difficult. Yeah. So let's consider the following ODE. So one-dimensional ODE. One-dimensional. Very difficult to solve. So that if you will do that, it will appear such a kind of, if you will try it, it will appear such a kind of arc sine, and then it will have a very awful the formula. But now, such a kind of the analogy which I told you before, give you much more information without integrating this, and which is these kind of things can do any biologist, any doctor, because they studied at least in gymnasium. So they studied at least in this is infocompetence. So then they learn in Ilkokula, so that to solve such a simple equation, they should do that. So then now we have again. Let's consider the function. So let's consider the following differential equation, which is this is nonlinear. And now, if you look in this term, this equation, that means f of y is equal sine of y. So the given function, because if you put here y of t, it will be f y of t, it will be sine of y of t. So that means the given. So we would like to solve this equation, and then for this equation, the f of y is the sine of y. Y prime is equal to f of y. Then what will be the phase portrait of this? We know that this will be. We have to now consider the function of the sine. Sine, we know the sine is the sine function as this form, right? So the function f has this form. So we have it in zeros. So what is what kind of equilibrium we have? We have 0. We have a pi, right? Because sine of y is equal to 0 will be equilibrium. So the f y prime of t is equal to sine of y of t. I say that when right hand side is equal to 0, all these the roots of the f of y. In our case, f of y is sine of t. All roots of the right hand side will be equilibrium by definition. That means we have the equilibrium 2 pi, 3 pi, 4 pi, and so on. So we have an infinite number of equilibria, and now it's difficult to solve this equation, to have the nice formula, exact formula, but I say I don't need that. So this phase diagram gives us the information, the behavioral solution around of this equilibrium. Right? Now let's just look Now I am interested the real solution, our solution. So this is a phase portrait, y prime y diagram, phase portrait. When I am speaking very up to this phase portrait, I am speaking the plane y prime. This is the phase diagram. And now, so this is I am interested in this equation. That means I know the function is f of y. I am considering the solution of y equals 0. This is equilibrium. Sine of y is equal to 0. We know that the sine is a periodic function. They have infinite number of zeros. And now, so this is my phase portrait. Now I would like to extract from this phase portrait information of my solution around of this point, around of this point, around of this point, around equilibrium. Therefore, I am looking here this P. So because I am interested on Y. Y here is the Y. That means this is the real solution. Y of T depending on T. This is the Y prime and Y. Now P. Let me just write it: 2 pi and 3 pi. So like this. So this is pi. This is 2 pi. This is 3 pi. So now look, now I would like to know the behavior of my solution. Now let's consider this behavior of solution around of pi. I am taking the point y0 from here. Here in the y0, this is my value of the function sine of the positive. Therefore, that means if this is a positive, that means y prime is positive because they are equal to each other. So that means that y prime is a positive, and y prime of t is a positive. At this point, that means the function is increasing, right? The function is increasing. That means if I am taking initial data from nearby p, the solution is increasing. And touch pi. So this is the cartoon saying. So the solution going to be increasing and going to this. And if I am taking the point around of 0, this is the function is this also positive from 0. This I have also growing up. But nearby of p, I am touching of p because the error is in this direction. Now, so now I know the behavior of my solution around of this equilibrium and this equilibrium. Now I am interested in the solution between pi and 2 pi, taking any point from here. If I am taking the point here, the value at this point is negative. That means the solution decreasing. If solution means decreasing means the value is become less and less. Decreasing means that the error going to in this direction. So the error going here, from here, and then here, and then here also. That means that from here, the solution, if I am looking for, the solution will increase to come to pi. So because this shows that between pi and pi and 2 pi, the solution is decreasing. And now between 2 pi and 3 pi, if I am taking any point here, then I am seeing that the value is the function, because this is the f of pi. F of y is sine of pi. The solution is the value is a positive, because sine is positive. The graph shows that the f of at the point if I am taking y0 from here between 2 pi and 3 pi, that means between 2 pi and 3 pi, my solution is a positive. That means f prime is positive. That means the solution, if I am taking solution going in direction of 3 pi. That means if I am looking this, the solution going like this. You see, I have, without solving such a horrible equation, then I can give the much more information how the behavior, the solution around of the equilibrium. Without solving, I am saying again, And again, this is the information without solving the equation, just looking the phase portrait. Of course, that means this picture show me that, so this point is stable, all right? This is unstable, stable, unstable, and so on and so on. All right? And but this is stable because around of these, if I'm taking the initial value from here, the solution converts to pi. If I am taking from here, also the solution converts to pi. From both sides, I am coming to pi. Here is not the case. From 2 pi is the solution going away. And then if I am looking here, between 3, 4 pi, then I will see the solution going in this way. That means if pi is 3 pi, pi, 3 pi, 5 pi, so these equilibriums are stable, the solution from both sides coming to him, and the 2 pi and 4 pi, 6 pi, and so on. So this is the unstable. Huge information, you see. Please, if you are a mathematician, please try to solve this simple differential equation. If you would like to solve this differential equation, you have to write this integral dy of sine of y is equal to the integral of dt. So you can just write dy of sine of y is equal to dt, and then if you are taking integral, this will be t plus c integral of dt. And this will be some kind of the arc sine and function. And this is even in the best case where you can have the integral of this. But nevertheless, having this, you have to, from arc sine, you have to receive the y of t. So the other goal is to find y of t. So huge way, and then it's very complex, and you don't have exact formula. But I don't need, I am looking these functions right-hand side. So I am looking y prime y. Y prime is equal f of y, therefore I am, instead of y prime, considering this, because y prime is equal to f of y. So this is the, I am looking to solve this equation. And then I am looking the taking initial data between nearby equilibriums and looking how the behavior, so please, this kind of question will appear in exam. So, and this is a very crucial for all of you. So then, if you are taking initial data from here, then you are putting the value, you are looking the value. This is sine of t, this is the graph of sine, and then at this point, the f of y is a positive. That means y prime is a positive, because y prime is equal to f of y. And then, if y prime is positive, that means fy of t is monotone increasing. Monotone increasing, that means y of t increase the value. The y of t going in this direction. So, beautiful. And now,
time is less than 1 minute.
Yes. Now we will have. So then, so we will. I will continue this after that. When will be the meeting will be end. Before I will start the continue, I would like to discuss with you the following. So then, I am foreseen to have the final exam on February 5 and February 5th. So the February 5 will be final exam. February 5. It will be final exam. And to help you and to give you the more information and so on, I will give a lecture till February 4. So, do you agree with them? Are you hearing me?
Yes, Hojam, I can hear you. Let us.
So how about that? I will give you the lecture till February 4. I mean the usual way, and then on February 5 you will have the final exam. What do you think then?
Sir, 1 minute. Let me check the schedule.
Okay, so then you can give me next lecture. I will look on it. Anyway, I will give, and if you will participate, it's good. If you will not, then you can ask somebody else. But anyway, so
On
please.
5th 5 there is a holiday hojam.
February 5th is holiday. February 5th, February 5. No, it's not holiday.
It's Friday.
It's Friday, exactly.
Okay, I mixed with my country. Sorry hojam.
So yes, okay. So so we are giving lecture in Turkey, so we have to follow. We have to follow the situation like here, right? And so anyway.
Okay,
next
week we will discuss with the other students, so
yes.
we will inform you.
Then I will look if the majority. Anyway, it will be helpful for you if I will give the lecture, because as you see in each lecture I am repeating what was before. And then this give you, you are having twice possibility. If you don't understood some topics, you can ask me and you can follow again and again. Therefore, usually in all countries, what I did, the lecture from for other topics, of course. So the students, and they were very happy. They try to learn more, and they will say that they will be with great pleasure. Of course, if they didn't have at that time exams, you know what I mean, for other topics, and therefore, if not, then please prepare yours. Anyway, I will give this lecture. If you, from one or other reason, cannot participate, this is also okay, because I will do my best to finish. So for those are from one or other reason cannot, so that I will finish in 28 lectures. But for those are interested to learn more, I will give also on February 4th. So it will nothing against on your schedule. So if those are interested in and also have a time to participate February 4, it's okay. So I will be give, and maybe you can ask, if those participate, you can ask some questions about the structure of the exams and so on and so on. So you will have additional information in February 4, because on February 5, the exam will be in the same spirit as I did mid-term exam. So, okay, go ahead now. Let's just continue our discussion. So what I say that instead of the solve this, now I'm speaking on 1D, all right? So I'm speaking on 1D. So instead of solving this equation, the 1D, the ordinary differential equation, which is called one-dimensional because we have only one unknown function y of t, which satisfies this equation with this initial data. And then I show that this is the phase diagram. Phase diagram is the helpful when we don't have exact formula for y of t. So, without solving this equation, we can say much more about the behavior of the solution, just having information of the initial data and the given function. So this is exactly, this can be done. This can be done for all people from the biology, medical school, and those are not mathematicians or even not physicists. So everybody who has you see, this is a very, very huge psychological effect. So in order to solve some, what does it mean solving equation? Solving equation, that means you have the exact formula, if you can, and you can, as a result, you have much more information on solution. But these simple examples show that you cannot have the exact formula in general. But our goal is not an exact formula. Our goal to say something on solution. The solution, how the behavior of solution. This is the goal of any differential equation. Any differential equation, any partial ordinary, the goal is to say the behavior of the solution, because all these equations we hope describe some very useful processes in disease propagation, in molecular dynamics, in ecology, in the medical process. And then our goal to say something, the behavior of the solution. Therefore, and this was a very psychological effect, which coming from the Poincaré is interested in the body problems, which cannot have the exact formula of solution. But he understood that the goal was the behavior of nearby of the equilibrium. And you see, we had two kind of function. You see, the function f is oscillating. You see, sine of y. Huh? So I am interested in this solution. Y prime of t is equal sine of y of t. Huh? The right hand side is f of y is sine of y. The sine of y is a oscillating function, all right? The solution is oscillating. The phase diagram of f of y is oscillating. However, the solution is oscillating, but I mean the right hand side is oscillating, but nevertheless, the solution is not oscillated at all. Solution, you see that either increasing, conversion to equilibrium, or decreasing. Again, conversion to increasing, decreasing. That's a general feature. Such a kind of question will arise in exam. I will give you some, I will ask you to construct some example, or I will give you the example itself, so, which will show that the function on the right-hand side is oscillating, but nevertheless, solution, the f is oscillating, but the solution is not oscillating. So this is a feature for 1D system. That means this is additional information which the mathematician didn't know when the ODE started. The 1D system, that means 1D ordinary differential equation, which you learn in the second or third semester. So if they will have the solution, even the right-hand side is the oscillating function, solution for 1D will never oscillate. You see? Either increasing or decreasing. So, of course, this must be proved. Now I am warning. So I am warning, and then this will be in favor of mathematicians. So the mathematicians, those are doing as expert in mathematics, they are really very happy people. This is really very, very happy people to be mathematician. Now I will explain why. Look, then again, you have ODE, simple ODE. Although this is not simple. So you have the function, the right-hand side, f of y, which is the oscillating function. And then you analyze, you find the error, how the error behavior around the equilibrium, and then having this information, then you can make a cartoon, the behavior of the solution and around of this equilibrium, and around this, you see, this is the stable equilibrium, because from both sides, the error going towards to him, you see. Here, this is unstable equilibrium, because around both of sides, the error going out from 2 pi. Here, it will be 3 pi will be stable, because if you take from here, we know the error here. If you take from here, the f of y at this point will be negative. That means if the fy is negative, y prime will be negative, because they are equal. So this is the value of psi. So that means y of prime at this point will be negative. That means y of t is decreasing. if this is y, decreasing means in this direction, increasing means this. That means around of this error will be there. That means 3 pi from here also toward to him, from here also to him. That means 3 pi will be stable. So this is you obtain from cartoon. That means that geometrical pictures, these geometrical pictures give you much more information. So then it's it could be it will be the temptation, and it was in the actually it was for engineering people, especially because they learn mathematics from mathematicians, because we are giving a lecture for engineering people, and then engineering people equipped with such an arm, which is called very strong arm, which is called mathematics. So they thought that they can do a lot of things without mathematician. In other words, they said that, okay, if I cannot solve this differential equation, which is mathematician doing a lot, I can just look the face portrait, and I can take such a geometric picture saying that everything is okay. Of course, this is giving you much more information, but this is only indication. So geometrical evidence is good, but is not good enough, and therefore such a kind. So now I would like to say to you, and then you will be see that the core what I am saying. I am a mathematician. Then you ask me to solve this equation. dy of dt, so y prime of t, this is the other notation. dy of dt is equal sine of y. In the second semester, on the third semester, you know how to solve this, the way. So the way how to solve this differential equation. If you are taking dy of sine of y, you are dividing, and this equal dt. You are writing this. From here it follows that this. And now you are integrating both sides, because from here it follows that. Now this is equal, the integral will be equal. So you are taking integral dy of sine of y is equal, the integral of dt is equal t plus s. And if you will compute this integral, you can easily find in the table of integrals, you can find the value of y of t is very complex way. And from there you have to extract y of t. And then you will have the very awful formula if you are happy. So then this is the way what we are mathematicians doing. And the engineering people and the biologists, if you are the medical doctors and equipped with this strong arm of the phase diagram, they are saying, this is rubbish, what the mathematician is doing. So I know that. So that this function has this form, f of y, and I am looking at the face portrait, and then for me it's interesting what's going on around the equilibrium, and then I can make this cartoon, and based on this I can say that how the behavior solution all that. Of course, if you will solve this exact formula, you will see that the behavior is the same, but this is the only half of story, and to show that, so the p is right, p phi of p stable equilibrium, at least is unstable. You have to make rigorous mathematical analysis. Saying that, so these are stable. Now I will in order to show that this is mathematically stable. So this error will be not enough. So this gives you information. Of course, you can, it's enough for engineering, they thought. It's enough for the doctors, they thought. But if you are saying these are stable, the behavior around of this equilibrium, in this way, you have to prove the mathematical. This phase portrait can say you, that I will touch in the next lectures, that this will be the direction this will be stable or unstable, how did the form. So this phase portrait, this is a good, but this is not good enough. In order to make a real things, you have to use the so-called stable and unstable equilibrium by the eigenvalues, which I will touch in the next lecture. And from there, you will see the behavior, and this phase portrait will give you information. After that, this phase portrait will be very useful. I will touch, but the engineering people and the doctors, they skip this. They are going in this way, and from this they are making some consequences. They are making some judgment, and therefore, in the history of our life, a lot of not a lot, but a couple of the bridges, they collapsed. So as I said, engineers trying to avoid to integrate this equation as a mathematician doing. So via this kind of the pictures, they make a judgment, and afterward they come in such a stupid. So I have seen this, such a stupid statement, and then after the collapse, a lot of things they take away. In Germany, there is the famous the firm which is called Siemens. So then, in nearby of the Nuremberg is the famous city where the war crimes people after the Second War received their what they did against humanity. So that in this Nuremberg, it was on the Sun firm and the Siemens, it was written, "We need mathematics, but we don't need mathematicians." Can you imagine? We need mathematics. That means so they should write this equation. They should write this equation. But we don't need mathematicians. Means they don't need to integrate in this way as a mathematician doing, as we are then considering this equilibrium stable or unstable using the eigenvalues. They say from here they are coming here. And the directions, and then from here they are making judgment, which is could work and could not work. So this is the geometrical picture. Geometric, it not only always means that you have to support this geometric picture with analytics. There the mathematicians are very useful. And without this analytical justification, the bridge which you bought with engineering, they could collapse. And then could lead to very unfortunate, to the lives of these some people. And therefore, after having in front of the door, we need mathematics, but we don't need mathematician. After 1 month, they take away, and they say that mathematics is a beauty. And that's why then you see then the mathematics is really beautiful things, and this helps us too much to understand the processes, and together with others, together with the engineering and the biologists and physics and chemistry people, we will have together these, and these will give us the beautiful pictures, beautiful information, and then in the next lecture I will show you the how to combine to make a marriage of the mathematician and the biologist, chemist, and all these people, which instead of the wrong statement, we need mathematics, we don't need mathematicians, it will be we always need mathematicians. And then based on this, this lecture I will conclude with the following. This maybe will appear in exam, but this is a very rigorous statement. The examples show that. So actually, this equation in 1D, one can prove this rigorous in mathematical way. In 1D equation, again. So 1D equation, irrespective of the given function f, has a parabola or cubic, if polynomial, or the oscillating itself function will never have the oscillation solution. Any solution for 1D will have a similar picture. Either will increasing or decreasing to the equilibrium. If you don't have equilibrium, they either will grow to infinity and plus infinity or minus infinity. Such a nice result, but doesn't help too much for the application. So very boring dynamics, because everything converts to equilibrium. Very good, mathematically beautiful result. So the function is a complex, but the solution is via this has a convergence to equilibrium, such increasing or decreasing. This is 1D, and we have seen in a ecological model, in the Lotte-Voltaire and prey-predator model by biofilms that this on the disease modeling. So we had the 2D systems. We had two equation, and we have seen for the models, the biofilm modeling, predator prey modeling, wolf and rabbit, the fish, and the Cerelius, and so the very predator fish. We showed that in 2D we had a periodic solution. That means if you remember,
Pardon, I'm very sorry to disturb you. My next lecture
Yeah,
will start after 5 minutes.
You have to disturb anytime. Go ahead.
Sir, after 5 minutes I have my next lecture. When we will finish?
Okay, so now I am finishing. You have to stay only 1 minute.
Tamam.
So then this is the information that for 1D we have the such we don't for 1D equation, irrespective if has a polynomial or if has the oscillation function, the solution has a very simple behavior. So the solution is not oscillated. In 2D, we have seen in our previous lecture, prey-predator model, the solution could have oscillated. So this is the crucial difference between 1D and 2D. And we see you next time. Thank you very much. Bye-bye.